We are in Chapter 8. Chapter 8 is studying momentum. In this unit, we will be looking at defining momentum, describing how impulse relates to momentum, classifying collisions between objects into two categories, and applying the concept of momentum to different sports and other sorts of things. Let's take a look at a question here and review a topic that we learned a few chapters ago. Which of the following has more inertia? A hippopotamus at rest, a hippopotamus moving, a beach ball at rest, or a beach ball moving? What do you think? Well, if you guessed a hippopotamus either way, yeah, ends up being A and B. It's a tie. A hippopotamus at rest is going to stay at rest. A hippopotamus in motion is going to stay in motion, and that is what inertia measures. So that's our answer. Let's do this again. Let's rank order the following from greatest to least in terms of momentum. We're going to contrast momentum and inertia. What do you think? What has the most inertia? What has the least? Well, it turns out that neither the beach ball at rest nor the hippopotamus at rest have any momentum. But a hippopotamus that's moving definitely has more momentum than a beach ball that's moving. So, what is momentum? Momentum is mass times velocity, and with the mass, we're measuring its inertia. And the velocity measures an amount of motion. So momentum really is a measure of the quantity of motion an object has. Now let's take a look at this question. Which of the following has more momentum? A speeding bullet or a kid on a bike? What do you think? Well, turns out these could be equal. They don't have to be equal, but they could be. Let's explore how that could work. Momentum, let's be reminded now, it's mass times velocity. So, we're not just talking about mass, and we're not just talking about velocity. If we take a look at the momentum of a bullet's mass is very small, but it has an enormous velocity. Whereas, relative to the bullet, a kid and his bicycle are going to have a lot of mass, but not near as much velocity. The two, however, when you multiply them together, they could equal out. Again, they don't have to, but they could. It's possible. If we're going to talk about changing momentum, we need to consider the two ways that we can do this. Since momentum is mass times velocity, we can either change the mass. I don't know how that would happen. If you were a car, maybe, and your gas tank was leaking, you could be losing mass. All right? I guess you're losing mass anyway. You're shooting mass out the tailpipe. But this is not the common type of situation. More often, we change the speed. If we're going to change the speed, that means acceleration. And acceleration requires a force. So changing momentum is going to require a force. Let's introduce a new concept, a new physics word. The word is impulse. The change in momentum will depend on two things: the size of the force applied and the amount of time the force is applied. if we want to change the momentum, remember we said we have to apply a force, but it also is dependent upon how long we're applying that force. We're going to define impulse as the force times the time. And here time is time for the force to act. Here's another question. If your car was stuck in the snow, would you rather have one guy push for 10 seconds or 10 guys push for 1 second? Think about that. Well, let's put things into place here. A change in the momentum is going to end up equaling the impulse. Remember, impulse is force times time, and momentum is mass times velocity. The little triangle there is a symbol that simply means a change in. Okay? So a change in the momentum will be given by the impulse. That's a new relationship that we're introducing in this chapter. And in this problem, or this question that I asked, it really doesn't matter if you have one guy pushing for 10 seconds or 10 guys pushing for 1 second. The force has to be multiplied by the time. If you have 10 times the force for 1 second, you're going to get the same answer as 1 times the force times 10 seconds. Right? Assuming all the guys push the same, I guess. And that will result either way in the same amount of momentum change. So in order to get that vehicle moving, to change its momentum, to get it some speed, maybe you'd need the 10 guys to push for 10 seconds. I don't know. At any rate, it's not it's not super difficult to figure out. It's force times time. That'll give you your change in momentum. The next thing we want to take a look at is collisions. Things smacking into each other. In collisions, momentum does not change. It is the same value before, during, and after the collisions take place. And that there are two ways that we can classify collisions. One way is elastic collisions, and the other way is inelastic collisions. In an elastic collision, we have an object that comes along, collides with another object, and then after that collision, it transfers all of its momentum, and that other object goes flying off. This could look different ways. In this next picture, we see the two objects are coming towards each other. They collide and then they go away from each other. And in this third example, the red ball is coming in faster than the white ball, but they are both moving. They collide, and a transfer of momentum occurs, in which the white ball now is moving faster and the red ball is moving more slowly. All of these have something in common. In all of these cases, the two balls collide and then go their separate ways. Here's the inelastic collision, and you'll see what we're talking about here. In this case, a freight car, I guess, is coming in at 4 meters per second, not real fast, and it's going to collide with another freight car which is just sitting there at rest. Okay, the collision happens, and the two of them now move away together. This is different. You can see why. Whereas in the previous example, elastic collisions, the two objects hit each other and then bounce off and go their separate ways. And in elastic collision, the two objects collide and stick to one another. That's it. That's the difference. We'll see more of this sort of thing, how momentum stays conserved, when we look at the lesson number 2, in which I do a little experiment with objects. Basically, we're going to wrap up by talking about a few applications. I think probably most of you have done the egg drop project. I think Mr. Hedquist does this in 8th grade. The impulse, or change in momentum, is the same regardless of whether the egg survives or not. But the thing that's going to determine whether the egg survives is the time over which that force acts. If the time is very, very short, such as an egg just landing on concrete, well, it's going to come to a very abrupt stop, isn't it? The time it takes to slow down is very, very short. That is going to yield a broken egg. However, if the time is extended by putting in some sort of padding or something, well, then the force doesn't have to be as large to stop the egg, and the egg survives. All right? Change in momentum is equal to the impulse. The impulse is force times time. In another video, you're going to look at follow-through. The author of our textbook is going to talk about how follow-through is important in sports, and how impulse is used to explain how different types of sporting activities work best. In bungee jumping, just think if we used a rope and you jumped off a cliff or a bridge and whang, came to an abrupt stop. No, you want to use an elastic band for this. The elastic band will stretch and basically extend that time over which the momentum changes, keeping the force small. That's it, folks. Until next time.